This is a lecture on the architectural elements of neural networks. And in particular, we're going to focus on convolutional neural networks and in detail the convolutions themselves. Right, so let's give ourselves a context. We're interested in thinking about neural networks in the context of classification. And so what that means is we might have an image of an object and we want to decide what is the object of. For example, is it a cat or a dog or a chair or a car, etc. So a common way to do this is with neural networks. And we could think of a neural network as a function which maps from images to a probability distribution over a known set of classes or categories. So here, for example, with the ImageNet dataset, there may be millions of images that are split into 1,000 categories. And for any image, we might get a probability over all 1,000 of those categories. And then if you were to ask the net, what is the most probable category, you just take the one with the highest probability. So the neural net and the convolutional neural net in particular will be built from a standard set of components. And these components are either linear or nonlinear. And the neural net itself is a composition of a series of linear and nonlinear operations. So linear operations include everything that can be represented by a matrix. And so these could be fully connected layers, which we'll talk about in a second, convolutional layers, or linear upsampling and downsampling of images. Nonlinear components can include activation functions, such as the RailU, which we'll also talk about in a minute, batch normalization, things like max pooling, which is like nonlinear downsampling, and softmax, which we'll talk about in a minute as well. So visually, we should think of the neural network as this. Like it takes an input image, and then some functional operations are applied to it, and then we get a series of values in some layer. And then that layer is going to have a series of linear and nonlinear transformations applied to it, and we get some set of values in another layer. And then we repeat this until we have the output. And so if we had 1,000 classes or categories, then our output would be 1,000 dimensional and may in fact be a probability distribution over those 1,000 dimensions. So here the neural net is organized in layers, and in a feed-forward net, each layer is really a function of the previous layer. And the particular architecture of these neural nets is subject to design by the user. They could, for example, all be fully connected, meaning that each neuron in each layer depends linearly on all of the neurons in the previous layer. Or if you're in the first layer, it depends linearly on all of the values of the image itself. Or we could have particular linear operations where not all of those connections are there, such as with convolution. So this neural network is going to have a series of parameters. And these parameters will be like the coefficients of the linear transformations for linear operators, or there may even be parameters for nonlinear components, which we'll talk about in a bit. All right, so let's first talk about the output of the neural net. And we'll recall that our goal is a probability distribution over the set of categories. And so a common way to use this, to achieve this, is via softmax and logistic functions. So here we could define a logistic function of z to be the function e of z divided by e to the z plus 1, or 1 over 1 plus e to the negative z. And this function is defined for all z in R, and if z is really big, then it's roughly 1. And if z is really negative, then it is roughly 0. So the softmax is a generalization of this function, and it's something which takes an input, which could be in capital N dimensional space, and gives an output in N dimensional space. And so these inputs are something called logits, and we might call them ZIs. This might be the direct output of the neural network. And these zi's, again, can be any real value, positive or negative, large or small. And so the ith component of the output of softmax is e raised to the zi over the sum over all j of e raised to the zj. And so you can verify that this is indeed a probability density because all of these are non-negative and they add up to 1. And what we see is that the output of a softmax, right, it's a probability distribution. And what it's really representing is, perhaps you could say it's the soft argmax. It tells you which component is the largest. So for example, if one of these z's is really large and all of the others are really small, then if you run it through the softmax, that value of large z is now a value very close to 1, and all of the other values are very close to 0. But if we have two equally large values in z, then in the softmax we're going to get like roughly a half a probability on each of those coefficients and roughly 0 on the others. And so in this sense, it's kind of like telling you which coefficient is largest, which is exactly what we want when we're doing classification because we want to choose the class of highest probability. All right. So we'll remember that it's a common practice to have nets actually output logits. And so because the nets are outputting logits, it's actually possible that when we train them, the optimization might not converge. And we could think of an example of this. For example, if you have linearly separable data corresponding to binary classification, and you want to solve this with logistic regression, then you could separate the data and the magnitude of this the magnitude of the sort of like logistic variable that you get could actually go off to infinity, and so your optimization is not actually going to converge. And what we can do is we can see this in application because we might be training a net, and then even after like 100% of training accuracy is achieved, the optimization can continue. And like test error can continue to change. And this is because we're really fine-tuning the logits. All right, so now let's talk about how neural networks think about images. Right? So we can think of an image as really a three-dimensional matrix or something which we'll call a tensor. Right? And so this has height, h maybe, and width, w, and c channels. And here, if we had a grayscale image, then c would be 1. If we had a color image, then c would be 3. And all of the internal layers of a neural network are sort of generalizations of this. They might have different heights and different widths, and they might actually even have a different number of channels. Right? So these could all have different values. Now, typically, we can't process all of our images all at once, and so we're going to operate on a batch of images. And so when you're coding in PyTorch or TensorFlow, then you're going to give as input to a neural network a batch, right? Or sometimes called a mini batch. Right? So what is a mini batch? Well, it's a collection of n images, which is to say it's a 4-dimensional tensor. So in PyTorch, the 0th component is the batch dimension, then the first component is the channel dimension, and then height, and then width. In TensorFlow, it's arranged slightly differently. The 0th is the batch, then it's height, then width, and then channels. So just make sure you're using the right convention in the software framework that you're using. Okay. So now that we know what an image is, we can think about what is a convolution and a convolutional layer. So let's start mathematically. So we might say that we have this convolution, S is equal to X convolved with W. And so the formal mathematical definition of this in terms of an integral is that the value of s at input t is the integral over all a of x of a times w of t minus a dA. So this is literally a convolution, and this, in a sense, is the inner product of x with a shifted and flipped w. Right, so notice that it's w of t minus a, and that's the source of the flipping. So here's an example. If w is just this square pulse and x is this square pulse, then you could think, what would happen as I shift and flip w and take the inner product of that with x? Well, I would end up getting this triangular pulse. Now, in machine learning and in deep learning, then the terminology that we'll use is x we might call the input to the convolution, and then w we might call the kernel or the filter, and then s, the output, we might call a feature map, or we might call an activation map, or we might call it something else. Right? So, of course, images are discrete objects, and so we need to write down, well, what is a convolution in a discrete sense? Right? So this would be the ith coefficient of s is x convolved with w evaluated at I, and so this is now the sum over all positions m, x of m times w of I minus m. So this is just the straightforward altering of that integral into a summation. And we could generalize this into two dimensions. So the convolution of an image x with a two-dimensional filter w evaluated at the ijth pixel. Right? So here we can say s of ij is the sum over all horizontal and vertical positions m and n of x evaluated at m and n times the w of I minus m comma j minus n. So this is, again, the same intuition that we're flipping w, and then we're translating it, and then taking the inner product of that with x. Now, there's a bit of unfortunate use of terminology. So here the convolution that we've said is really what a mathematician means when they say convolution. And so strictly speaking, the machine learning libraries actually implement something called cross-correlation, where they don't flip the kernel. This is really just a matter of convenience. And so mathematically what this means is that s, which is x convolved in a machine learning sense with w, is the sum over mn of x of I plus m comma j plus n multiplied by w of mn. Right, so this is like taking the kernel w and exactly translating it without flipping it. So visually we can see this as follows. Like, suppose my input is this 3x4 matrix with the letters A through L arranged as so, and then the kernel is this 2x2 matrix wxyz. Now if I take the convolution of this input with this kernel, then the first thing I get is I put the kernel in the top left corner, and so I get the inner product of the matrix ABEF with WXYZ. So then I'm going to shift the kernel by 1, so I get the dot product of BCFG with WXYZ. Then I'm going to shift it by 1 again. Then I'm going to repeat all this by shifting down by 1, and so here I get this 2x3 matrix. Now, when I say the dot product of two matrices, what I mean is just basically the dot product in the same sense as if they were vectors. So the matrix ABEF dotted with WXYZ is just AW plus BX plus EY plus FZ. So here, the key idea is that we're taking the kernel and we're translating it from top left to bottom right over one step at a time, going down one row at a time and computing all of those dot products. Now there's some extra technical jargon which we will see in papers where we might say we have a stride. So if we have a stride of 1, that means that this window we're going to translate by 1 each time we record the value. If we have a stride of 2, we're going to translate the window by 2 every time we record the value, and so on. All right, so now mathematically, convolution corresponds to an operation of multiplication by a Toeplitz matrix. So in particular here, convolution is a linear operation. So because it's linear, that means that there is a matrix which represents it. So if we want to write, say, in 1D, the convolution of the signal ABCD with the filter WX, we can write down what this would mean. So AW plus BX, then BW plus CX, and CW plus DX. And we can rewrite this matrix, this as a matrix vector product, where I have WX in each of the rows, but translated, or shifted, acting on the column vector ABCD. And so here, now, the filter acts as a Toeplitz matrix, where a Toeplitz matrix is one where all of the diagonals have constant value. Right? So there are nice properties of convolutions. For example, they're all diagonalizable by Fourier modes, at least in the circulant case. So we have to think about boundaries. And here, there are several choices that we can make. Right, so one is we could only include windows that are entirely contained in the input. And here, this is kind of like what we showed before. And here the issue is that the dimension of those images decreases. We could, if we don't want the dimension of our images to decrease, we could pad with zeros to keep the image the same size as the feature map, or we could treat the boundary in a circular way, or any various number of variations. And here, these are all implemented as flags in the convolution operation in like PyTorch or TensorFlow. So let's think about like exactly how convolution is working in let's say PyTorch, and here we'll dive into the conv2D operation. Right? So conv2D, right? So this is a two-dimensional convolution, is going to take a batch of images, and then it's going to give a batch of output activation maps or feature maps. Right, so let's remember our batch of images is really a four-dimensional tensor. So I have n images. There's Cin channels, which could be 1 or 3 if I'm acting on images, but in the inner layers of a neural network, it could be arbitrary other values. And they have some height h and some width w. Right, so the convolution operation is going to give an output, which is also a 4 tensor. Each image is going to be treated in parallel, and so that means n of the input is n of the output. But in principle, I could have any number of output channels that I would like. And I could also potentially have a different height and a different width due to how I treat the boundaries, what stride I have, etc. Right? So generally, the user-defined parameters here for the convolutional operation will be the filter size, the stride, and the boundary conditions that you want. And then those will determine the dimensionality h out and w out of the activation maps. So this is the input and output of a two-dimensional convolution as implemented in PyTorch. So let's think about, well, what is the filter in this case? Right? The filter is really a 3 tensor, right? And it's going to have 3 dimensions. It's going to have a height, a width, and a depth. And depth we should think of in terms of channels. Right? So let's zoom into just a single image in our batch. And remember that all images in the batch are treated in parallel. So a single image in the batch will draw us this 3D volume of height by width by Cin. And then we're going to have a convolutional kernel. And so that's going to have, say, height and width kx and ky, and the number of channels has to be Cin. And then this is going to give 1 channel of output. And then all of the outputs are computed in parallel. right? So the way this convolution is determined is you take now this three-dimensional block, the kx by ky by cn, and you translate it one row at a time, horizontally from left to right and top to bottom, over the input 3 tensor, and then we get an output 3 tensor. Well, really we get an output 2 tensor where the we get an output 2 tensor because this operation as written really gives us only one output channel, and so as we have multiple output channels, we get back that third dimension. And then we get back the fourth dimension from all of the images acting in parallel. Right? So it's important to think about like how many parameters and what are the free parameters in convolution. So if we're going to have a convolution with a filter of size kx by ky, and those are the user inputted parameters because C in is fixed by the input. And let's assume there's no padding, and we want to know how many parameters are in this convolution. And for now, let's ignore bias terms. Right? So just the strictly linear part of the convolution operator. Well, we know that, so we're asking what is the output size and how many parameters are there. All right, so the output size is n because each of the images are in parallel. C out is a user specified value, and so that sets that second or that that first component if we're zero indexing. And then we can ask, well, how wide is the image? Well, if I have a filter of width kx and I have an image of width w, then they're going to be w minus kx plus 1 positions horizontally where I can place the filter. And there's going to be h minus ky plus 1 positions vertically of where I can place this filter. And so my output will be this size. Now I could ask, how many parameters do I have? Well, we'll remember that all of the images are treated exactly the same, so I get no component from n. Each of the output channels are computed in parallel, and so I just get a linear term in C out. And the filter size is this 3 tensor, which was kx by ky by cn. So here the number of parameters is C out times kx times ky times cn. Now, I encourage you to think about what happens if I add bias terms. And for bias terms, you should think, like here we had a linear operation, like some like general linear operator A acting on input. And so the bias is really A acting on input plus B. And so then you can think about, well, how many parameters are in that bias term. All right, so the reason that we have convolutional layers, there are several of them. One strength of convolutional layers is that they have many fewer parameters than fully connected layers. So let's remember a fully connected layer was where every value of the input affects every value of the output in a linear way with a parameter that is estimated at training time. Right? And here the convolution is saying that only these nearby pixels or activation values affect this value of the output. So there are many fewer parameters than fully connected layers, and what that means is that it is cheaper to compute, so you can operate on larger images, for example, and also there are benefits in the actual successful completion of the optimization that you get as a result. But there are other like conceptual strengths based on what we understand about how images work. And this, one of these strengths is equivariance to translation. Roughly speaking, any feature of an image, if it's in the top left, should be treated as the same if it's in the bottom right. So that is to say, if we're building a cat detector and the cat is in this part of the image versus that part of the image, the same properties of a cat should be reflected. Another way of saying this is we shouldn't have to teach the neural network that this blob on this part of the image is a cat and that blob in that part of the image, the same blob in a different part of the image is also a cat. we can hard code that in to the neural network architecture itself via the convolutional layer. So visually, we can think of these convolution layers as feature detectors. And here you should think of the kernel as having some pattern or some shape of high values and low values. So here I have an example drawn where I have this small kernel which has this sort of like a vertical line as its filter. And so then now as you translate this over the image that's drawn on the left, which is just this full circle, then you're going to get very high values at the left edge and the right edge of that image where it aligns quite well with the kernel. You'll get small but non-zero values everywhere else on the circle, and then you'll get zero values completely off the circle. Right, so here, this is like an edge detector, a vertical edge detector as drawn. And generally, we'll see that in neural networks, the kernels are quite often detecting a meaningful shape, like an edge or a corner, or at higher layers, combinations of shapes that might be something like an ear or a nose. All right, so that is the convolutional layer. So now let's move on to talk about some of the nonlinear layers. Right, so we'll start with activation functions, and we'll start with the most popular activation, something which is called the rectified linear unit, aka the RailU. So here, this is the function sigma of z equals max of 0, comma z. So this is like the linear function, but it's rectified to always be non-negative. We could alternatively do other rectifications. For example, we could use the absolute value rectification. And here, you could think like, why would I want to do this? Well, perhaps you might be doing object recognition in images that you want, and you want your system to be invariant to image reversal. And so then you might be able to bake this information into the very activation function of the neural network. There are other activation functions that subsume these two, such as the leaky RailU, where sigma of z is some, let's say, alpha I of the minimum of 0 with zi, and plus the max of 0 with zi. So here, this has a unit slope to the right of 0, and then some other slope alpha I to the left of 0. And then alpha I could potentially even, could be fixed, or it could even be learned. And you may get performance gains if you throw this parameter alpha into the pile of things that you're learning. Other activation, nonlinear activation functions, you could use sigmoids. For example, you could use logistic or the logistic function or the hyperbolic tangent function. Generally speaking, these are not recommended for internal layers, hidden layers of a neural network due to saturation. And what that means is that if your z is located in like the flat regions of this sigmoid, then you're going to get very, very small gradients. And then you might just never get out of those regions, or it might like take you a very large number of iterations to get out of those regions. Now, there is a case where sigmoids are recommended, and that is often as the last layer, and that could be seen as basically like computing the softmax of the output of the layer. And here you could say, well, what about the saturation issue? And this can actually be compensated for by the choice of the loss function when you're training the neural network. All right, so another very important nonlinear component of neural networks is batch normalization. And we should think of batch normalization as a technique for improving the speed, reliability, and performance of the optimization of neural networks. So roughly speaking, what batch norm is going to do is it's going to take some input and give some output. And the input, it's going to first center, and then it's going to rescale so that it's a unit unit variance. And then it's going to allow itself to scale that quantity by some parameter gamma, and then translate that quantity by some parameter beta, which is learned. Right? So again, it takes the input, it centers it to 0, it scales it so that it has unit variance, and then it's going to then add learned parameters which can compensate back for the scale and for this translation. Right? So here, if the input is x, we could say compute the expectation of x, or the average value of x, which is computed from the input, subtract that from x, and then we're going to divide by the square root of the variance of x. And remember that the variance of x is like the expectation of x minus its mean squared. Remember, the square root of variance is the standard deviation, and so roughly this is dividing by the mean of x, or subtracting the mean of x and dividing by its standard deviation. Now, you'll notice that there's this epsilon term that's in there. So really, we're dividing by the square root of the variance of x plus epsilon. So the variance of x is computed from input, but the epsilon is fixed and is some small and fixed number. The reason that the epsilon is there is to make sure that this quantity is differentiable everywhere. And if we had a 0 value of epsilon, then it is possible, if x was the input vector of all zeros, then we wouldn't know what we mean by the output of batch norm in that case. Right? So an important thing to note is that batch norm doesn't really change the expressivity of the neural network, right? So translates and scales, and then it adds back a learned scale factor and a learned translation. Right? So it can really compensate for the effect that it had. Right? So one thing that we should ask when we think about batch norm in practice is, what are the dimensions that it is operating on? Right, so we should think of batch norm as treating channels separately. And so then the expectation and the variance are computed over particular slices, and that's the slice of n, h, and w. So that's graphically depicted in this figure. So this three-dimensional volume, the vertical direction is height and width together. Then the other two directions are the channels and the batch number, the number of the image within the batch. So batch normalization is called it because you're averaging over the batch itself. So within a single channel, you're averaging over all positions and all items in the batch. And so what's shaded is the region of computing this expectation and variance. Right? So here, this normalizes across images in the batch and across positions or pixels in an image. Right? The reason for why normalize across these directions, of course, you could make other choices, but remember that in a convolutional net, we're really believing in this equivariance principle, which is to say that we should treat pixels at different parts of the image the same. So then if we're going to normalize across a batch, then we need to do that in a way that treats different parts of the image the same. And so that's why we include the position dimensions in the section that gets normalized by batch norm. So this tells you basically generally what's happening at batch norm. And then an interesting thing to think about is, well, what happens at test time? Right here, if we go back to the formula for here, we might say we have our input x, we're subtracting its average and dividing by its variance, and this variance is computed over a batch. But at test time, we only have a single image going into our neural network awaiting to be classified. And so then what do we mean by the variance in that case? Right? And so this leave for in-class discussion. All right, so batch norm is a very complicated object to study. We could ask, why does it work? So it's been shown to be extremely effective. It's one of the most common architectural elements in neural networks. And so it begs an explanation of, well, why does it work? So the original paper that introduced it offered the following explanation based on something called internal covariate shift. And so what that roughly is the change in the distribution of network activations due to the change in the network parameters during training. That's how it was defined in that paper. And roughly the idea is that modifications in an early layer of a net could cause very large changes downstream, and batch norm would decouple these effects. So for example, like changing the parameters in the first layer could significantly alter the mean and variance in a later layer, but because those are normalized and some scale factors are put back in, then that layer is not going to be subject to as much change as it would be without the batch normalization. Right? Now, this is the rough explanation. This explanation is disputed, and there are other works out there that say the batch norm is not due to internal covariate shift and is actually due to other effects, for example, by smoothing of the loss landscape. So we'll talk about batch normalization in class when we read these particular papers. All right, so hopefully this, this lecture showed you a couple of the most common tools, the common building blocks for a neural network. And our real big takeaways are, right, the neural network is a series of linear and nonlinear functions composed together in a sequence. And there can be many, many types of those linear and nonlinear functions, which we combine in ever more complicated ways. Right, so what we saw in this lecture was just the fundamental building blocks, so like linear layers, fully connected layers, convolutional layers, and then the nonlinearities, such as the RailU and batch norm. So then these can be built up into very impressive and complicated, like, entire architectures, and we'll talk about those in a subsequent week.